impact those different functions. So the first thing we'll talk about is increasing and decreasing functions again. Yesterday we talked about how if you've got successive y values that are increasing or decreasing, you can identify your graph and identify an interval in your graph in which your graph is increasing or decreasing. And this is the best way of saying it. It's the algebraic way of saying it. I think people struggle with phrases like this that are written algebraically, because it's not good enough for us to say, well, increasing by definition or in regards to a theorem is just when your y values get bigger, okay, or just when your x values get smaller. Sorry, y values get smaller. We need something better than that, and that's what these two statements here say. Okay, it says f is increasing. F just being your general generic function, whatever you might want it to be. Okay, on the interval I. Okay, so the interval I is just some arbitrary general generic interval on the x-axis. Okay, so you're just viewing some arbitrary interval, and that's what they usually say when you have an arbitrary interval. They call it I. It says if f of x sub 1, if f of x sub 1, so that's a y value for some x value, okay, is less than f of x sub 2. Well, that's another y value for a second x value. Does that make sense? Okay. Whenever x1 is less than x2 in your interval I. So what they're saying is whenever this is true, whenever your x1 that you're using as an input value is smaller than your x2 that you're using as an input value, and when you input those and you get f of x sub 1 to be less than f of x sub 2, that means that this y value associated with that x value, okay, they come first, and they are smaller. The y value is smaller than that y value that's associated with that x value, okay? So it provides this picture right here, okay? This x value here, x1, is less than x2. Would you agree with that? To the left of it, right? And they're saying f of x sub 1, its y value, is less than f of x sub 2's y value. If that's the case, whenever that happens, your function is increasing. That's the test that we could use to make sure that's increasing. Okay? F is decreasing. Okay? It's the exact same phrasing, but now we say, well, if f of x sub 1 was greater than f of x sub 2, so your first y value is greater than your second y value, okay, then your graph has to be going down, and we consider that decreasing. Okay? Throughout a lot of the homework that I've given you, they're going to ask you a series of questions to state the interval in which a function is increasing and decreasing. Just basically you start left to right, okay, and you start thinking about moving, put yourself on that graph, and you want to move from left to right all the way through the graph, walking on that graph, okay? So what would you be doing from here to there? Decreasing, okay? So the way we write that, we're going to write our interval of decreasing and increasing in regards to what x values that is happening. So the x values that we are decreasing on are, since we got that arrow, we're going to go from negative infinity, right here, negative infinity up to 1, okay? So this is decreasing, okay? Does that make sense? Then, from here, from there to there, what are you doing? Increasing, okay? So I'm going to put my increasing column here. Okay, so and I list the x values. So from 1 to 3, 1 to 3, we are increasing. What are we doing from 3 to 4? Yeah, 3 3 to 4, you're decreasing again. Okay? So 3 to 4. And then from 4 to what? We're increasing again. 4 to infinity. Okay? Usually when we identify increasing and decreasing intervals, we leave them as open intervals. Okay? Meaning that we do not use square brackets for the endpoints. Okay? Because at that point 1 comma negative 1, at the point 3 comma 1, and at the point 4 comma, I don't know, like 0.8 or something like that, we're in that transition period. Does that make sense? We're not increasing or decreasing at that point. These points, okay, because this point right here, okay, is, would you agree that that y value of that point is smaller than any y values around it? Okay, so on some small interval, in regards to the y values around that point, it is the smallest y value. Okay, so what we do is we call that a minimum value, and often you call it a local minimum. Okay, local meaning for that little window where I've circled that point. Okay, the values that are around it, the local values that are around it, that one is the smallest. Okay, if that's a local minimum, what do you think we would call that one? That's a local maximum. That y value is larger than the infinite number of points that are kind of in its neighborhood. Okay, so that value of 3,1 is a local maximum. Okay, and then here we've got another local minimum. Okay. When you get into calculus, you'll do something called the first derivative test and the second derivative test. And those tests will give you a technique for quickly identifying where a function is increasing and decreasing, and to quickly find those local maximums and minimums. Right now, we're gonna mostly deal with finding local maximums and minimums from a graph. Okay. But we'll also be able to determine in a particular function how many local maximums or minimums we might have total. Okay, so that's going to be kind of, we're going to investigate that on a deeper level here in a little bit. Going through and talking just to show you. Thought I had a slide here. Well, those are referred to as local minimums and local maximums. Okay, but there could be what we call absolute maximums and absolute minimums. Okay, and that is when we look on a closed interval. Okay, on a closed interval, we're going to try to find out what is the largest f of x value or largest y value on that closed interval. Okay, so if I look at this one. All right, so this is a closed interval, so we're looking at those points from -1 up to 2, 2. And hopefully you recognize that this is the largest y value of the entire graph, right? Okay. Where in the last one we had largest y values in just comparison to the things that were near it. Okay. This is now referencing the entire graph, and that is then called an absolute maximum. Okay, it is still a local maximum. Does that kind of make sense? It's still a value, a y value that is larger than anything in its neighborhood. Okay, but comparing it to the whole graph, it is also larger than anything else on the graph. Okay, so some of your local maximums or local minimums might actually eventually be absolute maximums or absolute minimums. This point here, the lowest point on your graph, absolute minimum. Okay, and we see from time to time these things kind of bouncing back and forth, and we want to identify those points as maximums, minimums, absolute, or local. Okay? Sometimes the word global is replaced with, or replaces absolute. So you might see the phrase global maximum or global minimum. It just means, global means the whole thing. Does that make sense? Okay. So what would you call that point right there? Okay, I'm going to call that an absolute maximum because it is the largest y value on the graph, right? Okay, and it's the same because it's the same as that one. Okay, so we're going to say both of those would be absolute maximums, but they're both also local maximums, correct? Okay. What would you, and this is really the reason I wanted to show this one, not necessarily for the absolute maximums or local maximums. What do you call that point? That's a local minimum. Okay. But what do you call that though? Absolute. That's the absolute minimum. Okay. Okay. And it is the absolute minimum because it's a closed interval. We're able to identify what that ordered pair is. Does that make sense? If that was an open dot, okay, we would have trouble identifying what that ordered pair is. Okay, so that's why when we talk about absolute maximums, absolute minimums, we want to look at a closed interval because potentially the absolute maximum and absolute minimum could end up being the endpoints of that curve. Okay, and we want to include those in if that's the case. If I look at this one here. Okay, so what do you call that point? That's a local max. What's this one? Local min. What do you call that one? Absolute max. Sorry, min. And this one? Absolute max. Okay. What do you notice happens at local maximums and local minimums all the time? Phrase that. I know what you're saying, but phrase it better. What is happening? Well, what we talked about so far. What is happening as we move that way? It's increasing, and then from there it's decreasing. Is that what you're saying? Okay, you transition from increasing to decreasing or decreasing to increasing, right? Okay, and that's what calculus will allow us to do quickly. Is it will tell us that the second derivative test will quickly tell you that hey, to the left of this point you were increasing. Don't care what the y values were, but you were increasing, and to the right of that point you were decreasing. So if I was increasing, and then to the right of that I decrease, that tells me that point should have been a maximum. Okay, and then likewise, if I go from decreasing to increasing, that tells me that point should have been a minimum. Okay. It does happen as well on some like absolute maximums. We still have one there, right? Okay. But this absolute minimum down here, we don't have that transition, right? It's just you're continually decreasing until you get to that final resting point. Does that kind of make sense? Absolute maximums, absolute minimums, increasing, decreasing. When you write your increasing, decreasing functions or intervals for your functions, on the WebAssign, they are wanting you to put commas. Took that in the email, but don't put commas in between your intervals. So if you got 3 intervals where it's increasing, write one interval, comma, the next interval, comma, the third interval. Okay. We could use unions, but for some reason they're not using that notation in the homework. Okay, at least that's the way it kind of looked as I was going through it.